To answer this question, let's look at our factoring theorem that says a polynomial p has root k, in other words p of k equals 0, if x minus k is a factor of p of x. So if we have a polynomial p of degree n, the fundamental theorem of algebra tells us we have a root. Let's call that root k1, and p of k1 is 0. Now the factoring theorem tells us that p of x equals x minus k1 times some other polynomial q of x. And what's the degree of q of x? Well, we saw that the degree of p has to be the degree of x minus k1, which is 1, plus the degree of q. So since the degree of p is n, and the degree of x minus k1 is 1, we get that the degree of q must be n minus 1. But now, again by the fundamental theorem of algebra, q must have a root. Let's call that one k2. And the factoring theorem tells us that q of x can be written as x minus k2 times some other polynomial, w of x. Now, we can rewrite our original polynomial p of x as p of x equals x minus k1 times q of x, which is x minus k2 times w of x, where the degree of w of x now is n minus 2. And we can continue this, rewriting w of x as x minus some other root k3 times t of x, which has degree 1 less again, n minus 3. And this continues n times until we get down to degree equals 0, because then the fundamental theorem of algebra doesn't give us a root. But that's because it's just a constant. And this constant a is going to be our lead coefficient, because if we multiplied this all out, our coefficient of x to the n would have to be a. So we can conclude that if the roots of p of x are k1, k2, k3, all the way up to kn, with lead coefficient a, that p of x can be written as a times x minus k1 times x minus k2 times x minus k3, all the way down the line for every single one of our roots until we get to x minus kn, our nth root. Notice that this is very similar to the factored form that we got for quadratics. The only difference is that with quadratics, we only had 2 roots, where here we have a degree n polynomial with n roots.